As systems continue to increase in both size and complexity, the ability to drill down and find the root causes to failures continues to be a growing challenge. Many of the traditional methods to compute low-level reliability or maintainability statistics in complex designs and bring this data to the system level to address system requirements conformance is becoming increasingly costly and challenging. While contributing lower-level designs may be developed to satisfy their own specific reliability and maintainability requirements, the complex integrated system should also be able to observe and manage failures within these integrated systems expeditiously, effectively, affordably, and safely. This video exploits areas within traditional design development processes that systemically contribute to the growing sustainment challenges resulting from pursuing independent and often competing interdisciplinary assessment objectives. This video will also describe the new and powerful corroborative nature of the Integrated Systems Diagnostics Design, or ISDD process, by the embracing of new interdisciplinary trade space, uncovering untapped ROI from the balancing and reusing of these interdisciplinary design assessments more inclusively and seamlessly within the implemented maintenance solution. After we represent each design discipline, as it is traditionally contained within its own circle in this Venn diagram, we will describe the general objectives of each discipline and how their independent assessments products are characterized to service the sustainment goals of the fielded system. Let's begin by examining the circle that represents the reliability design discipline. For large complex integrated systems, reliability engineering is an essential analysis process that must be worked concurrently with other design disciplines and should be started early in the product development phase. It can be performed very extensively and consistently, or it can be performed to respect the individual talents and preferences of the individual engineer. For complex systems, it is performed to meet system requirements, which typically involve many tools and techniques that often vary from organization to organization. While interoperability between heterogeneous reliability assessment tools and products remains a challenge from and between subsystem designs, the goals at the integrated system level are to remain unchanged. Fundamentally, reliability engineering contributes by performing analyses that will best predict the expected reliable serviceable life for each component used in the system. The discipline must also account for how, when, and the critical nature of any of the failures for any system components and what is the result or impact from the failure throughout the integrated system. While this is an oversimplification, this is the basis for computing many reliability products such as component or design failure rates, failure modes, failure effects, mean time between failures, criticality or severity of failure, as well as a number of higher level reliability-based assessments, including the FMECA, RPN, and FTA analyses, which are often performed within the reliability engineering discipline to drive the reliability-centered maintenance sustainment paradigm. Maintenance engineering contributes the information on how the design is to be maintained when any failure occurs or before a failure is expected to occur to ensure that the product or system is able to perform or function properly when it becomes needed for operation. Additionally, maintenance engineering must provide the knowledge on the expected duration of a corrective maintenance action or repair activity, which may include the time expected to isolate, remove, procure, and replace the failed item. While this is an oversimplification, this is the basis for computing such products as mean time to isolate, mean time to repair, mean logistics delay time, and operational availability, to state a few of the more recognizable metrics. The discipline also may assess tools and methods to minimize similar future failures by tracking, reporting, and learning from corrective actions performed to maintain fielded systems, or by making those corrections during the runtime operations that simply manage or mitigate failures, the failures as they occur, or pending imminent failure occurrence, based upon an observable failing condition. While the fracas sustainment paradigm is shared benefit between reliability, maintenance, and diagnostics engineering, its value is significantly constrained due to its belated involvement and its attempt to leverage frozen design characteristics. PHM or any health management sustainment paradigm, on the other hand, must be worked earliest in the design development process to ensure the design is able to effectively manage observed failing conditions. Diagnostics engineering is a process that is best when worked at the very earliest stages of design development in order to influence the design for sustainability. This is a tremendously valuable opportunity that plays a significant impact on the effectiveness of any selected approach to any serious health management paradigm or system sustainment philosophy. When that opportunity isn't currently available, diagnostic engineering can still greatly enrich the ongoing diagnostic capability of complex legacy systems by first establishing the design's diagnostic capability baseline. This can immediately ensure that the design is much more embracing of future design modifications, requiring integration with evolving and new technological advancements and testing or sustainment paradigms. Eventually, the captured design will allow the diagnostic assessment data to be reused on related future designs or repurposed to for a wide variety of future cost leveraging opportunities. Diagnostic engineering is a discipline that provides proactive sustainment options for future designs, paying dividends throughout the life cycle of the fielded product or system. It has tremendous impact on the utility of the data products produced from the investment into the reliability and maintenance engineering efforts. This discipline determines if failures can be detected or isolated and how to optimally devise an approach to observe or discover those failures to ensure the correct failure is indicted and remedied in a timely fashion. It offers unmatched insight to the validation of bit effectiveness and any health management or PHM design integrity at the integrated systems level. While legacy designs can be greatly enriched at any time by capturing the design knowledge in a form that can be leveraged for continued system lifecycle diagnostic benefit, captured design knowledge can also provide a jump start in concurrent variant designs and also new designs. Ideally, the ISDD activity needs to be performed iteratively within the development process so it can be used to assess and influence the design from a diagnostic perspective, ensuring that the goals it shares with reliability and maintainability engineering are balanced and maximized continuously throughout the life cycle of the fielded system. The early involvement of diagnostic engineering will ensure the design is influenced for sustainment approaches, because the data generated and investment into the producing of the assessments from all of these design disciplines are no longer marooned to solely address specific requirements. Instead, the investment into these assessment products work to form a balanced knowledge-based asset that is able to be carried forward directly into being an active component in the implementation of the sustainment solution. The timely performance of diagnostics engineering will provide improved fault detection, reduced false removals, retest OK, CND, reduce false alarms, reduce systems, mission aborts, lower maintenance costs, effective isolation to optimum repair level, operational availability, and the ability to uniquely isolate critical failures. That is, to proactively discover where test points or sensors are unable to discern between the root causes of any low-level component failure due to inherent integrated system design or health management constraints. When ISDD is performed within a corroborative design environment, systems, reliability, maintenance, and diagnostics engineering activities engage in data sharing and leveraging in a synchronized manner using identical and shared data artifacts, repeatedly cross-checked for integrated design fitness in terms of consistencies, completeness, and omissions, while being performed much earlier within the design development process. Metrics owned by each independent discipline have traditionally served to score or assess how each discipline is able to meet its independent disciplinary requirements. In this traditional manner, it's difficult to realize how these independently owned requirements often serve cross-purposes and they're competing against those metrics and requirements serviced by the companion disciplines. For example, if the objective is to reduce false alarms, we may increase mission success, but it may then increase false removals, when the design was not optimized to allow for optimized fault detection, which may thereby increase the cost of ownership in terms of requiring excessive spares for non-failed components, that is, components with a substantial remaining useful life. Since diagnostic engineering provides the knowledge of fault group constituency, we would know when we reach the constraints of diagnostic capability and must remove a fault group or set of suspected failed items in order to remediate. However, if we try to minimize investment in diagnostic engineering, our replacement may be incorrect and not fix the failures, or even mask the non-detectable failures and thereby increase loss of system availability. Many of these valuable assessments are not possible without the inclusion of high-end diagnostic engineering. Learning from fielded experiences is useful, but it is a reactive measure and should be intended to be used as a method to use empirical data from tracking sustainment activities to supplement the design knowledge base. Please view the video on DSI Workbench to investigate the optimal value of simultaneously leveraging both design-based and empirical knowledge in sustainment activities. As we move towards more complex or critical systems, diagnostic engineering provides proactive design influence and will always be of tremendous value that keeps on returning benefits, specifically when worked in the Integrated Systems Diagnostics Design, or ISDD, as a corroborative development process. ISDD ensures an approach that collectively services the interests of each independently owned design discipline, interdisciplinary or interorganizationally throughout the design development process, balancing to the overall goals of the integrated system design. Through this nearly inadvertent corroborative data sharing and leveraging environment, we slice through the competitive nature of each independently owned discipline and discover new value for starting ahead on every follow-on development, for concurrent variant designs, or for ensuring new designs and sustainment supporting technologies. This concludes this video on realizing interdisciplinary value of ISDD. Be sure to view other videos showing how design data is captured and simulated in an operational environment, or simulated results that consider the impact of maintenance on any fielded systems. The stage simulation will produce rather shocking results that really exploit the effects of our design's diagnostic integrity. What can be foreseen in various implemented sustainment solutions including maintenance troubleshooting, PHM effectiveness, system safety and system readiness, or any costing, based upon any deployment and sustainment paradigm.